Hi there, grade 11s. In this video, we are going to look at an object on a flat surface where the applied force will be acting at an angle to the surface. So this is the second video in a series, and in my first example, we are going to look at an object that is stationary on a horizontal surface and the F applied will be acting at an angle to the horizontal. Right, here we go. So I've got my object. The gravitational force acts on the object, Fg, which can be calculated by taking mass times gravitational acceleration. And there is a normal force acting on the object, but now this normal force will not be equal to the gravitational force if and when the applied force is a pulling force at an angle to the horizontal plane. The reason for this is that the applied force adds a horizontal component to the plane. So this is F pulls X component, and it's got a vertical component. And in this case, if it's a pulling force, the F pull has an upwards vertical component or a Y component. Now, these two components has an effect on the friction. So the friction will still be acting in the direction that will opposes the attempt to move. So the object is stationary, and we've got static friction if the object is stationary. If the object is stationary, the forces are in equilibrium. In this case, the Fs, the static friction, would be cancelled out or balanced by the pulling force X component. How do we get the X component? We have perpendicular components of the F pull. So the angle theta and the X pull is adjacent to each other. So if we have to use mathematics, trigonometry, then this would be the F pull cos theta. So our static friction can be calculated by determining the cos of theta and multiplying it by the pulling force. Right? Let's move on to when the object is just going to start moving. Sorry, I better just add all these forces in a free body diagram. So in a free body diagram, you've got your gravitational force, you've got your pulling force, which is F applied. You've got a normal force, and you've got your static friction. In the second scenario, the object is about to move. In that case, the friction is Fs max. Right, let's draw the scenario. I think you should be familiar with the force diagram now. I'm going to concentrate on the free body diagram. So you've got your object, and we've got a gravitational force that can be calculated by saying mass times gravitational acceleration. You'll have a normal force, and I'm deliberately drawing it shorter than the Fg. You've got your applied force at an angle, of theta, and you've got the friction that will oppose the motion. And in this case, this friction is the maximum static friction. Once again, the maximum static friction is in equilibrium with the applied forces X component. And the applied forces X component is F applied cos theta. So Fs max, if you have the correct information, you could calculate it by using this equation. There is another way though, because Fs max is in relationship to the normal. Now, this is where matters are a bit more complicated, because the applied force has a vertical component, and the two vertical components, F applied y, and the normal force acting in the same direction, upwards, is kept in equilibrium by the gravitational force. So in this case, the normal force would be equal to, let me do the normal force separately. The normal force and the component of the applied force in the y direction will be cancelled out by the gravitational force. So the normal force would be equal to Fg, the gravitational force, minus the applied force's y component. How do you get the applied force's y component? To get the applied force's y component, the purple one in the diagram, you need to see that the applied force is opposite the angle theta. So it can be calculated using F applied sine theta. So our normal force here is equal to the mass times gravity for gravitational force minus F applied sine theta. So Fs max is mu s times mg minus Fa sine theta. Sorry for squashing everything together. So this is another equation for calculating the maximum static friction. I want to do an example where the object is being pushed. That's our next example. So example number 3 is the object is about to move and the F is applied is a push and the friction would be Fs max. So we've got our object on a flat surface. Let me do both. Got our object on a flat surface. There is a gravitational force acting on the object. There will be a pushing force on the object at an angle. Theta. Now the friction would oppose this applied force and it would be Fs max. The normal force now, normal force would be much more than the gravitational force because the applied force has a downward component here. The F push Y is down. The F push X is to the right in my diagram. So this is the F push X. To draw the free body diagram, we've got the gravitational force, Fg. We've got an applied force at an angle of theta. We've got the friction, which is maximum static friction. And we've got a normal force that will balance or cancel the gravitational force with the Y component of the pushing force. So let's see. What are the possibilities? The Fs max is in equilibrium with the pushing force's X component. And the pushing force's X component is F push. It's adjacent to the angle theta, so we need to use cos theta. Because we are working with Fs max, that's not the only option that we have to calculate Fs max, because Fs max is also in a relationship with the normal force and the static coefficient of friction. Now, the normal force, if I can look at the normal force separately, the normal force will be in equilibrium with the gravitational force and the Y component, because they of the pushing force, because they are going, those two forces are going in the same direction, downwards. So to zoom into the normal force, it is mg plus, and the Y component of the pushing force is F push sine theta, because the y component is opposite the angle theta in the triangle. So we've got Fs max is equal to mu s times mg for the weight and F push sine theta. Good. In the next video, we'll look at the kinetic friction part of this situation. Thank you for watching. You're welcome to join my channel. I cover from grade 8 right to matric examples and questions and concepts, mostly to help learners in the high school. Thank you very much.